Okay, so here we go. All right, so we had MO diagrams here, and there are a bunch of people, there was a check definitely for each MO diagram, and all you're doing is taking the electrons from each atom and basically putting them in the MO diagram following Aufbau principle, lowest energy level first. You never have to write these, okay? But you have to take particular care of whether this is NO, NO minus, in this case NO plus. Any case, here we have nitrogen and oxygen, and you say, well, which one is which? It doesn't matter, but for fun, this, of course, is going to be your oxygen. Okay, why? Well, 2p4 gives it away. All right, 2s2, 2p4. But notice it's lower, which means it's more stable. Why would that be? Because, well, oxygen has one more proton, higher Z number than N, so it contracts the what? The orbitals more. Hey, that's kind of fun to think about, but maybe you don't need to. Bottom line is you've got to put all electrons together. So if you notice the 2s, you have a total of 4 electrons that come in. There's only 4 positions they fill. It's pretty simple. Here we have 4 plus 3, so you get a total of 7 electrons. 6 fill the bonding orbitals there, okay? And then, of course, you fill 1 extra that has to be forced into that higher energy anti-bonding orbital. And, of course, to get bond order, you take all your bonding electrons, which are in bonding orbitals, which are always the lower position of each diagram, 2, 4, 6, 8, minus the electrons that are in anti-bonding. 2 and 1 is 3, so 8 minus 3, divide by 2, you get 2.5. Okay? Same thing over here, but now it's NO plus, which means one of the 2 atoms we're starting with is going to have 1 less electron. So I made this one have 1. It was 2p4, 2s2, 2p4 for oxygen. Okay? I took it from here. You could have taken it from here. The bottom line is there's a total of 6 electrons that would fill, based on the Aufbau principle, the lower energy positions first, which these are the bonding orbitals, and same scenario here. And so when you do the bond order, you get what? You get 8, 2, 4, 6, 8 minus 2, 6 divided by 2. Why divided by 2? Because each bond is a pair of electrons. And you get a bond order of 3. Okay? And now you're off to the races. Okay? But some people didn't know that they had to put all the electrons in. And you go from lower energy positions until, like in this example, you're forced to put it in a higher energy position. Okay, well, you're going to get, in the next test, another set just like this. Of course, it's not going to be NO, which was confusing enough when I was grading this, because no was the answer for some of them. But in any case, who has a higher bond order? Well, this one does. This has less bonding electrons, anti-bond electrons, that destabilize, or this one has more electron density as a wave function in between the 2 nuclei, so the bond order is higher. Yes?
Should I rotate the iPad because the left side is kind of cut off? Can't really see the question.
It's actually a wide angle.
Okay.
It will take into consideration. Thanks for thinking that way. Yeah, it looks like it's cut off because it's showing 4-3, but it's taking long. I don't know why it doesn't do that, but I'm tall. In any case, moving on. Who have a higher bond strength? Well, because the bond order is higher, it takes more energy to break apart NO plus than it would be what? NO, okay? Because this has more bonds, okay? Or a higher bond order, which means there's more electron density between the nuclei. And of course, because this has a higher bond order or more electron density between the 2 nuclei, the 2 nuclei will be pulled in closer because they attract more of those electrons, and the bond length would be shorter. Shorter bond length, higher bond order, higher energy to break the bond. Okay, and you should go through this unscathed. That's pretty straightforward. So if you messed up on that, make sure you don't, because that is straightforward. You'll see that again. There's no if and buts, but a few no's along the way. Okay, who's paramagnetic? Paramagnetic means that we have unpaired electrons, right? In this case, all electrons have been paired up. They're in filled orbitals, which means the electron spins have been canceled, except this one right here. This one, you have one lone electron that's unpaired, which means it's lone pair. There is no another electron with an opposite spin to cancel that direction of that spin, which means this one creates a magnetic moment, which means it will be attracted to one of the 2 poles of a magnet. So who is paramagnetic? The one that has a lone pair. that one. And for reasons that you just say, hey, it's got a lone pair. It's got a single electron in orbital. That's enough to explain that. Okay? So that should have gone, that's a lot of checks right there. It should be. All right, who has resonance? Well, as we learned in other theory, valence bond theory, when you have a fractional bond order, that means electrons are delocalized, which means you don't have 2, you don't have 3 of something in between. Something in between means electrons are moving within the molecule. They're delocalized, partly because there's probably an unhybridized P. Allow me, bless you. Thank you. All right. So the one that has resonance is that fractional one. Okay? And we saw that with valence bond theory. Okay, justify your order, delocalization is key with resonance. And in this sketch, very much like this is the rat quiz we took, okay, where you had to pick which one was which. Now I'm asking you to draw it. And what do we know? A molecular solid. I know people are weak on this area, that's why we're going over the homework we're going to go over and talk about and do this, but the molecular solid is molecules that are attracted by intermolecular forces. For instance, classic case, how does water make ice? This is a finite molecule. I say finite, that's the exact number of particles, atoms that make that particle into that bent shape, sp3 hybridized. And that will produce an electron deficient H. This pair of electrons is held so close to the O, remember O, F, okay, and N, are so electronegative, they have a high Z number in a small enough space to pull that pair so close, you're really dangling a proton because what? Hydrogen has 1 electron and 1 proton. So that's really a proton attracting another water molecule. So ice is a molecular solid. It sticks together by, in this case, H bonding, also dipolar in LDFs, by intermolecular forces of attraction. And they're always going to be weaker than bonds. So, because you have single molecules, the MO diagram would just be for a single molecule. And if you have a MO diagram of a single molecule, okay, the gaps are going to be big between the bonding and anti-bonding orbitals. So big that they can't absorb wavelengths alike, have color, and so big that these guys make too big of a gap. And electrons do not freely move to this conductive band, this band where they can freely move. Electrons are not delocalized in water. Okay? So the gaps between molecular solids exist because they're molecules. They're not interconnected. You need to have interconnectivity. You need to have delocalized electrons to start stacking them. Now, in metallic bonds, copper, notice we say copper, and people say, well, that's just an atom. Well, you never say in copper wire, hey, that copper wire is exactly, okay, 10 million atoms, and you don't write that as a chemical formula. You would never do that. It's just copper. So anytime you see a chemical formula of an element that's a metal, that's metallic bonding. And what do we know what that is? Well, we've studied the what? Face-centered and body-centered cubic structures. The cubic structures that we studied were the actual radii, or I should say in this case, the nuclei. And the electrons are free to move throughout this crystal of ions because they create gaps that overlap. Now why? Well, when you have copper bonded to copper bonded to copper, because they're all interconnected by their electrons, you're putting more copper here, which means you have what? More boxes. And the bottom line is, this starts stacking into a continuum that what? Overlaps. So electrons that are in a lower energy can freely, without any energy, move to a higher energy. These gaps are so big, and it's important because it's called band theory. All of the copper atoms are interconnected by these electrons that their MO diagram stacks. You don't have this with water because it's just an O and two H's. That's it. There's no other interconnection. Here, every single copper atom is in this diagram. So it creates a huge continuum with virtually no gaps, and electrons are able to pass through. And this explains the conductivity of copper. It's a metallic substance. Okay? So, that was important that you get that. Now, if you're weak on your types of compounds, no worries. After today, it should be easy enough to understand. Okay, better attitude. So, moving forward to the next page, and this is where the disaster really started for most people. The multiple choice.
Oh, God.
Yes. Now,
It's such a fun time with those.
what I was after was you to identify a couple different things. First and foremost, the top three, A, B, and C, were molecules. How do I know? Well, when you draw the structure, and these are carbon skeletons, these are called structural formulas that organic chemists use. Every corner is a carbon. They don't show the H's, but by showing the shape, you can guess the hybridization. Hey, that's a triangle, sp2, sp2, all right? This would be sp3, even though you don't have, okay, that, okay. So you need a double bond to have sp right there. But in any case, the bottom line is these are finite shapes, shapes that are defined by every nonmetal becoming that octet, okay, and getting stable. This is a continuum of carbon bond to carbon bond to carbon. A little different. This is not a molecule. This is a network of covalent bonds. This is ions dissolved in water. So there's some differences here. Let's go through them. Which chemical species above would undergo crystal field splitting that results in visible color? Crystal field splitting means I have an ion that is so charged and so small that it pulls in what we call ligands, not next to them, but it pulls them into their d orbitals. So these are transitional elements, okay, that are highly charged. Now, why are they highly charged? Well, as we've learned already, transitional elements, number one, have smaller radii than the more active metals because they have a higher Z number. Now, we know that there's shielding in the D and it keeps them constant. We've been down that road. But a lot of the transitional elements, because they can't gain enough electrons or lose enough electrons to become noble gas configurations, they have a play on their S and their Ds. Okay? But what's really striking about them is a lot of them have high positive charges. For instance, we dealt in lab with potassium permanganate, which is really the MnO4 ion, group 1 ions dissociate. Well, we learned that this is +7. Whoa! That +7 attracts the negative end of water so much that negative end of the O actually will go into some of the d orbitals. Some of them will not, and that breaks up the d orbitals. So crystal field splitting is for transitional elements, okay, that have d orbitals of unfilled electrons. So if you think about, let's do something a little easier. Let's think about iron for a second. Iron is 4s2, 3d6. So if I draw an orbital notation, okay, 4s2, 3d6. Okay. We know that it's going to lose the what? To make iron +3, it can lose the two S's because, as we know, the 3D is N = 3. It's closer to the nucleus. It shields for the S. And because of electron-electron repulsions, iron doesn't have a high enough Z to stabilize that. It loses this one. So, it's got a good number of what? Z. This makes it small enough, and it's +3. This thing is pretty small. Being so small, the negative end of the polar molecule, one of the pairs, is pulled into iron. Now, iron has d orbitals. Here's one d orbital. There's the very famous, the one I like, the pacifier. Let me draw another one. Remember, L equals what for D's? 0 for S, 1 for P, so L equals 2. That means it has two preferred axes. Whoa. Well, here's one, here's another. Here's another d orbital. I'll draw another color. I'm not going to draw a 5 because I'm not sure if I can. Here's one. So here's another, okay? So these are two d orbitals. And there's, okay, 3 others. Bottom line is, only 6 water molecules can fit around the iron. That's why you see that right there. 1 water molecule will be pulled in there. Now, 6 water molecules, only 6 because 7 would be too much strain. So only 6 can fit that close. Kind of like our octahedral shape, right? 1 on top, 1 on the bottom, and the 4 in the middle. Okay? So it's really an octahedral shape. Bottom line is, some get pulled directly into an orbital, some get pulled in between an orbital. And what that does is the electron pair of oxygen will take some of these that go directly into the orbitals and destabilize that orbital pair. So 2 get directly pulled into the orbital, and then the others are in between. So these guys are not as destabilized as much, and what we've created, party people, is a small gap that can what? Absorb wavelengths of light. Okay? So, crystal field splitting that would cause, notice, that results in a visible color. Booyah, right there. Gave that away by that diagram. Why not this guy? What does zinc have? Yeah, it probably undergoes crystal field splitting, but definitely does not give off a color because there's no place for electrons to move to. That's why zinc is sometimes considered not to be transitional, and that's why zinc is colorless. Yes?
But isn't like in that form an ion?
Yeah, but I said that results in a visible color.
So like zinc plus 2 wouldn't give off a color?
No, because although it may attract waters enough, I'm not sure if it does or doesn't, but it can't because the Ds are absolutely filled. To be a true transitional means you have unfilled d electrons. So anything with filled electrons.
So it would lose the 4s instead of the...
Yeah, definitely use a 4s. But then you have, although it may split like that, have a gap, there's no place for electrons to go because they're all filled. Okay? That's why that was a little bit tricky. 9. Which molecular solid? Ions, network of covalent compounds. Hey, ions of nuclei have mobile free electrons. These are your molecules. They're definite finite particles based on covalent bonds. These are your molecular compounds. They're not ions in water. They're not a crystal of covalent bonds like diamond, that's what this is, or graphite, okay? So out of these, would probably have the best opportunity to absorb wavelengths of visible light. So these guys are colored. Which one's a dye? For a different reason, but very similar. The reason why iron can, because it creates a scenario where you have a gap, okay, and electrons can move by crystal field splitting. We create a smaller gap. Now what did we learn? These guys could have color for a whole different reason. They're going to create a small gap for an entirely different reason, and we need MO theory to explain them. What did I say about the what? Metals. The metals, because they're interconnected by their delocalized electrons, all of the silver stacks up. Now, for these molecules, what's interconnected? The double single is called conjugation. That means every one of these guys has an unhybridized p that electrons are able to move throughout. Every one of these carbons and nitrogens are going to be stacked, we call this pi stacking, but it's okay, in the same MO diagram. So if I have more of these, then these guys do what? Start creating a band, a continuum. And if that continuum, if there's enough double single, enough conjugation, enough delocalization, this continuum becomes big enough and the gap gets small enough for the same movement of electrons to this band. These guys can give off color. These are called chromophores. They give off color for the same reasoning. We're wearing them. They're in our flowers. Okay? They're in our lamp tomorrow. So party people, that's important. So which one would probably best absorb wavelengths of light? I gave you 3 possibilities. Well, the one who has the greatest amount of double, single. The one with the greatest number of carbons and nitrogens that are interconnected would give you the biggest band and smallest gap. That's why C is the answer. Anthracene, which by the way is mothballs, okay, is white, doesn't have a color. Just not enough conjugation. Are they stacking? Or the gaps are too what? Gaps are still too big. This one has even more, right? So the gaps are smaller, but still not enough to absorb wavelengths of light. So this is a dye. This is a chromophore. I would never have you memorize which one is, but I just want you to realize the more conjugation, the more chance for stacking, pi stacking. Okay, that's all that was. Who's a network solid? A network solid, for those that don't know, is nothing more than covalent bonds that continue in a crystal fashion. Graphite's an example, so is diamond. Okay? They're a little bit different because they're not sticking together by attractive forces like these guys would. They're sticking together by a continuum of covalent bonds in all directions, which gives them huge, huge melting points. Okay. 11. Which molecular solid would have the highest vapor pressure? Vapor pressure, party people, is the force upward due to molecules overcoming their attractive forces and escaping. It's the pressure upward. It's what moves the pot that you're boiling, making some boiled water or pasta. Okay? So who would have the highest vapor pressure at the same temperature? Who evaporates easier? It's another way of saying who has the what? Weakest intermolecular forces. Those that evaporate the fastest have the weakest attractive forces. The reason why we don't smoke in a gas station, good idea not to smoke in general, is that at a gas station you have hydrocarbons you're dispensing. Hydrocarbons are LDFs only, weak attractive forces, which means they evaporate very easily. You have what? Combustible vapors all over that place. Okay? So, who has the highest vapor pressure? Well, who would have the weakest intermolecular forces of these three? If you look, there's some polarity here. These definitely LDFs are pretty strong, but they definitely have some polarity. So they have dipolar forces. Okay? This one would actually what? H-bond with itself. So this is LDFs. This has dipolar and would H-bond with itself. This would have the what? Strongest IMFs and the lowest vapor pressure. This one would be the second, and if you notice, this one is all nonpolar, only LDFs. And by the way, it's lowest number of electrons, so it's probably the least polarizable. So that's your answer. Okay? Number 12, excluding the molecular solids. Gone, my molecules. Which solids would not conduct electricity? Well, we know that these guys will. Just talking about them. Right? Their bands overlap. Diamond does not conduct electricity. Okay? So, excluding the molecular solids, which the solids will not conduct? Well, we know free ions do conduct. Moving ions conduct. We know that, what? Ionic compounds, because their ions are not free, can never conduct. But you dissolve them or melt them in an aqueous solution, electricity can be conducted by the movement of charge. Okay? This doesn't conduct. And why? Well, diamond is sp3. It doesn't have an unhybridized p to allow the interconnectivity of what? Electrons. There's no delocalized electrons. Which means what? The gaps are going to be too big. And it would need too much energy to get to that conductive band. Whereas what? Okay, sp2 hybridized graphite, okay, has an unhybridized p. Allows delocalization, which means in your MO diagram, you're going to have pi stacking. It creates small enough gaps. And that's why graphite does conduct. And that's one of our conductors that we use, or what? It's one of our electrodes in our electrolytic lab we did earlier in the year. Okay? So moving forward. Now we're going to get to, these are actual multiple choice questions from a previous, recent released AP exam. So in any case, based on the data above, which of the following liquids has the weakest intermolecular forces? Well, look at the vapor pressure. Don't get lost in equilibrium pressure. Equilibrium just means in a container. Let them reach equilibrium. That's how we actually measure vapor pressure. We'll talk more about that when we get to equilibrium. But the bottom line is, who has the lowest vapor pressure? This one. Which means, okay, It has the, I'm sorry, they wanted which of the following has the weakest intermolecular forces that would have the highest vapor pressure, right? So if you evaporate the best and have the highest pressure going up, then therefore, my friends, you're going to have the weakest intermolecular forces of attraction. 14, where's H bonding? So many people picked this one. That's a covalent bond. That's an intramolecular force. One inter between molecules. That is not an appropriate H bond. Remember, an H bond is what? Electron deficient H. This is pulling that pair, so you basically are dangling a proton. A proton would not attract another proton. So no, there's your H bond. The positive proton, electron deficient H, which pulled off, is attracting this negative. Remember, oxygen. Think about it. N equals 2, right? Small orbitals. Highly dense negatives. This thing's really going to attract it. So that's why D is the answer. All right, moving forward. Another question. You got 2 boiling points. Clearly, these have no polarity. They're just LDF forces. And what we learned, things that have more electrons are more polarizable. And therefore, the IMF between them, or the LDF, only have LDFs, are so strong that the boiling points, okay, are so high. And that's the reason why iodine can exist as a what? A crystal. We've seen this with our copper iodine lab. It's basically a crystal of molecules. Okay? It's not a network solid. But what do we know about iodine? It sublimes. What's sublimation? Hey, I2 solid becomes I2 gas. Why? The IMFs are not significant enough to become a solid, but still weak overall, because they're just LDFs, escapes as a gas. And that's how the iodine got to our copper. Okay? Looking at these 3, you see the butane just has LDFs. The acetone has LDFs, of course, an electron cloud, but because it's polar, it has some dipolar. And then propanol has the same attractive forces, but it can H-bond with itself. Acetone cannot. Acetone does not have any electron deficient H's. These electrons are essentially right down the middle. And so this nucleus, this area here, is not a positive proton. All right, so because of having more attractive forces, okay, butane is less than acetone, less than 1 propanol, and as Ellen said very eloquently, if you just looked at the next question, you could have answered those questions. Okay, and as I said that in my other class, like, oh, really? Okay, yeah, possibly.
I didn't even notice that.
That's okay.
I need all the help I can get.
All right. So now we get into the descriptive part of the test where a lot of people went astray. 2 points I have to make here. Number 1, unless we're breaking a network solid, which is a what? Covalent bonds of atoms. When it comes to melting and boiling points of molecular compounds, we're talking about intermolecular forces of attraction. So if you mentioned the word bonds were broken, it's just wrong. I don't read anything further. You get it all wrong. You do not understand that molecular compounds stick together by their finite particles by attractive forces. They don't stick together by bonds. Even though these attractive forces are significant, they're never as strong as a bond. So that's important. Number 2, if I said to you, explain the boiling point difference between butane and chloroethane. Butane has a 0 boiling point, chloroethane 12. And you said, well, butane only has dipolar forces. I'm sorry, butane only has LDFs, and left it there. I have to mark it wrong, because you didn't explain what chloroethane has. You need to speak to both of these. So what do you know? Butane is only what? LDF forces of attraction. Chloroethane, okay, has LDFs, but it has an additional force of attraction, which is what? Dipolar. And having that additional force of attraction gives it higher, complete, total intermolecular forces. And that's how you answer that question. By the way, the key is posted in Power School to look at this closely. Okay? So that's that. Now, the next 2 questions. Solubilities. Taught you last week, you've probably learned before, solubility is when 2 chemicals that are soluble is because they have similar attractive forces. If something can mix in a liquid or as a gas, because gases and liquids are considered to be fluids, if they can mix and interact, or if they can mix homogeneously, it's because they have similar attractive forces. And more so, we're talking about liquids here because gases tend to have weak attractive forces. But nonetheless, okay? So, explain the water solubilities of chloroethane and acetone. Well, if you look at your chart, we know that acetone is soluble. Okay? Acetone is soluble, and chloroethane is insoluble. So that means that something about acetone makes it have similar attractive forces. Well, if we look at acetone, okay, acetone, I'll get rid of some of this stuff. Acetone has LDF forces just like anything else because it has a what? Cloud of electrons. And I guess I use my hand because I don't know where my putting. So
Paper towel.
yeah, paper towel. I'm okay. So if I look at acetone here, which is a carbon double bond to an O, the CH3 group, CH3. Okay, it's got a cloud of electrons, so it's got LDFs. Of course, so does chloroethane. They're both polar, so they both have what? LDFs. But, unlike chloroethane, this very electronegative atom could H-bond with the H of water. It cannot H-bond with itself. We talk about boiling points. But in water, it's soluble or miscible because the electron deficient H of water can attract that O. Remember, H bonding occurs with an electron deficient H that's attached to an oxygen, a nitrogen, or what? What's that? Fluorine. And that creates a scenario where we really have, in this case, a proton attracting another very electronegative atom of an O, N, or F. So it has an O that the H can H bond to. So it can and does dissolve in water completely because it can interact with similar attractive forces. It cannot take this H and attract the O of water. That does not happen. But this part does. So it does H bond with water. Which meaning what? Water has H bonding, dipolar force, and LDFs. Well, with water, so does acetone. That's why it's soluble. Chloroethane can LDF with water. There's probably some attractive forces in an emulsion layer. It has dipolar forces, but it doesn't have the H bonding ability because the chlorine isn't electronegative enough. And by the way, N equals what? 3. It's too big for those reasons. Okay, but again, you needed to explain that all the way through. Explain the water solubilities of butane and 1-propanol. Same thing. Butane only has LDFs. 1-propanol has LDFs, dipolar, and H bonding. So because propanol has the same attractive forces as water, all three of them, it's miscible or soluble. You need to talk about both of them and lay it out. I allowed it if you said, hey, you know, 1-propanol can H-bond with water, butane can't. I allowed it, but I won't for the second time. Lay out, butane only has LDF forces. Water has LDF, dipolar, and H-bonding. Therefore, 1-propanol, which has all three like water, is soluble, has similar attractive forces. Okay, water sticks to itself because why would it attract to something weaker? Okay, that's that. And number 20. Explain the boiling points of acetone and 1-propanol. Well, as we talked about, acetone, when we talk about boiling points, careful. This is acetone attracting itself. It has electron cloud, it has LDFs, it's polar, has dipolar forces, but what can it not do with itself that it could do with water? H-bond. So it can H-bond with itself. Whereas 1-propanol, okay, for 3 carbons, has that OH group. It has electron cloud, LDFs. It's polar, dipolar, but it can H-bond with itself. So therefore, its boiling point is higher. If we bring back a table that we use for the regions, okay, a much simpler test somewhere, somehow, okay. Table H, propanone is another word for acetone. Notice its vapor pressure is much higher. Its vapor pressure equals the atmospheric pressure, so at this point, so its boiling point, remember boiling point was when the vapor pressure equals the atmospheric pressure? So its boiling point is lower than the other liquids. Ethanol, an alcohol, OH group. Water, H's and O's. Ethanoic acid, okay, also, all three of these H bond. This one only does what? LDF and dipolar. These guys do LDF, dipolar, and H bond. They resist evaporation, okay? So finishing this up, hopefully. Great question here. 21. The known boiling point of chlorine is 238, but HCl is 188. Given that information, explain to me the difference in the boiling point. Why can chlorine, who only has LDF forces, hey, it's Cl and Cl, okay, have a higher attractive forces, has to be if the boiling point's higher, resist boiling, right, than HCl, who has 188. But this is LDFs and dipolar. This has two forces, this has one only, yet the boiling point is higher. The IMFs are higher here. Only thing you can say is what? The LDFs of the Cl2 are so much higher than that of HCl that the total amount of IMFs of the Cl is greater than that. The LDFs overtake both of these attractive forces combined because the LDF is so much higher. And why? Great number of electrons. Most of you got this right. It's pretty good. So here's a case where you don't always say, hey, having dipolar forces always beats LDFs. No, here's a case where just the LDFs alone were great enough because of the great number of electrons. Okay?
Could you ever mention like the shape of CO2?
It was more about the electrons and the shape. They're both very similar shaped, right? They're linear, two atoms. Greater number of electrons means what? More polarizable. Last question. SO2 melts at 201. SiO2 melts at a huge leap. What is so different about silicon dioxide? It must be bonded continuously with covalent bonds because it takes a lot more energy to what? To break bonds than to break what? Intermolecular attractions. I was after that this has IMFs only to break apart. This must have had bonds. That's what a network solid is. Covalent bonds. It takes more energy to break apart. And this was a lot like the last question on Thursday night's homework. Okay? So in any case, that's that. You have this as a key to go over. You're going to get exactly a replica of this. Of course, the questions will change, but the same concepts are there. Okay? Yes?
How are you supposed to know that's a network solid rather than ionic just from the formula?
Well, because that silicon, okay, is so close to this side. It's actually a metalloid. It's on the staircase.
Yeah.
So anytime you're going to have, okay, guys in this area, okay, there's not going to be a transfer. Their electronegativities are too similar. So, generally speaking, you're going to have covalent bonds between the metalloids. Right. It has to be a huge difference in electronegativity to have the ionic. There's always exceptions, but that should be a clear case of, okay, I see why you would say ionic, okay, but being in the same area would mean that they have two similar electronegativities, therefore it would be network.
I just have a question. Number 21, were you, like, did I have to measure the electrons? Because I said the LDS were stronger than the polarity and the other LDS.
I think I was looking for electrons.
Oh.
Why the electrons are greater.
Yeah, that's what I was
Yeah, I think I needed that little piece.
Okay,
You got other parts right, but I was looking for that.
Okay.
Started this.
Yeah.
Oh.